morning and welcome to this next lecture on vibrations of plates and shells. Last time we looked at a plate that was simply supported on all edges, okay, and we found that this was the final mode shape, a sinusoid in both the directions, okay, and its resonances were given by this expression. The mnth mode had this as its resonance frequency or natural frequency. Okay. Now, along the same lines, if we now have the other two edges clamped, so this is simply supported, this is simply supported, but now this is clamped and this is clamped. Okay. So we proceed in the same fashion. The u3 of x comma y is some function in the y direction and simply supported in the x direction, okay, and then we substitute and acquire the polynomial in y. Those steps are the same, and y of y finally acquires this form: a cos hyperbolic rho 1 y by b plus b sin hyperbolic rho 1 y by b plus a c cos rho 2 y by b plus a d sin rho 2 y by b. And what are the clamping conditions? The clamping conditions are u3 for all x at y equal to 0 for all time is 0, then u3 for all x at y equal to b comma t is equal to 0, then the slope del u3 by del y for all x at y equal to 0 comma t is 0, then lastly del u3 by del y for all x at y equal to b for all time is 0. And this translates to the condition on y. So y looks like, okay, y at 0 is 0, y at b is 0, dy by d small y at 0 is 0, and dy by dy at b equal to 0. Okay, these are the four conditions. Okay, with these four conditions, again you will get a matrix equation for A, B, C and D, and this has 1 0 1 0 cos hyperbolic rho 1 sin hyperbolic rho 1 cos rho 2 sin rho 2 0 rho 1 0 rho 2, then rho 1 sin hyperbolic rho 1 rho 1 cos hyperbolic rho 1. This term is minus rho 2 sin rho 2, and this term here is rho 2 cos rho 2. This is equal to 0. So again, for non-trivial values of ABCD, that means all not 0, if this has to be satisfied, then the determinant of this matrix must be 0. That determinant ends up looking like twice row 1 row 2 cos hyperbolic row 1 cos row 2 minus 1 plus row 2 square minus row 1 square sine hyperbolic row 1 sine row 2 is 0. Okay. All over here you have k's in them that has to be solved for, and there will be many k's. Okay. So there will be many kn's, n going from 1 to etc., for which this equation goes to 0. Okay. Once kn is known, then you can figure out your natural frequency omega n a square root of rho h by d is equal to m square pi square and kn. Okay. So omega mn can be known. Okay. Now again, in here you need to find the corresponding mode shape. That means A, B, C and D need to be known. Okay. So now for a kn value where this matrix becomes singular, okay, again one equation becomes dependent. Okay. You will get only 3 independent equations, which means 3 of these constants have to be solved in terms of the fourth. Okay. So in this case B, C, D are solved in terms of A. Okay. So you can see that A plus C equal to 0, you can see, which means A is equal to minus C. Okay. Then and so forth. Okay. I do not want to elaborate, this is the simplest equation. So now you can see here that A and C are opposite. So I can put this as minus A. Okay. Then row 2 will and row 1 both will acquire the n index. Okay. Row 2 will acquire the row 2 n index, row 1 will acquire the row 1 n index, and similarly you can solve B and D in terms of A. Okay. The details are there in the text. So then what happens? The expression for the mode shape, okay, the expression for the mode shape becomes u3mn x comma y is equal to A comes outside cos hyperbolic rho 1 n y by b minus cos rho 2 n y by b. So A and C have been taken care of, minus rho 2 n cos rho 2 n minus cos hyperbolic rho 1 n by rho 1 n sine of rho 2 n minus rho 2 n sine hyperbolic rho 1 n. Okay. Now this corresponds to B and D. So you will get sine hyperbolic rho 1 n y by b minus rho 1 n by rho 2 n sine rho 2 n y by b, this entire thing in the y direction into sine m pi x by a. Okay. So, this is the mode shape. Again it is indeterminate up to a constant. Okay. This can be determinant when forcing is taken care of, when forcing is put in. Okay. So, now we have looked at two conditions where we have simple support at the x0 xa and simple support at y0 and yb, and we have also simple support all around. And next we have looked at simple supports and clamped. Okay. So, for these two mode shapes I will animate the shapes and show you in MATLAB as I did for the beams. Okay. So, let us go to the MATLAB screen. Okay. So, let me open here. Now, there are two indices, so I have to take care of both. So, this is simply supported all around the first M1 and 1 mode. Okay. And each index now will talk about half cycle. So, one half cycle in x direction, one half cycle in the y direction. Okay. So, you can see this is the 1-1 mode of a simply supported plate. So, you can see that displacement is 0 all over, okay, and the slope is unhindered, which means moment is 0. Okay, this angle is unhindered, it is not 0. So, the other component moment is 0. So, this is the 1-1 mode. Okay. So, you can see that you get as a profile one half cycle along this direction, one half cycle along that direction. Okay. So, let me now shut this. So, I will increment one of them. So, I will increment the n to 2. So, you will have two half cycles in the y direction and one half cycle in the x direction. Okay. So, this is the x, you get one half cycle, whereas in the y you are getting two half cycles, okay, one going positive, one going negative. And so, now there is a node line, okay, midway along y there is a node line, there is a 0 displacement point over here, okay, and there are two antinodes along y, maximum displacement points. Next, I will shut this. Let us make it 2 2 in both directions. So, you get two half cycles in both directions. So, you can see that. So, for every mode the same boundary conditions, simple support along all edges. So, what this means actually is, if you can give an initial displacement in this shape, okay, exactly in this shape, and you let it go, then it will vibrate in that shape at the natural frequency forever. So, this is a 2-2 mode. So, 2-2 has its own natural frequency. So, if I can give this plate an initial displacement in this shape and let it go, let it free, then it will oscillate ideally forever at that single natural frequency of the 2-2 mode. Let me close it here. One last, let me do a 2-3 maybe, 2-3 maybe, or 2-4. So, 4 half cycles in Y, 2 half cycles in X. Okay, so it gets complicated. So, along X I have 2 half cycles, along Y I have 4 half cycles. Now, I would shift to a plate which is simple support and clamped. Okay. So, let me do again the 1-1 mode here. So, as in the second case, 2 opposite edges are simply supported and 2 opposite edges are clamped. Okay. So, let us run it. Okay. Now, this is a bit subtle, you have to. Okay. So, along Y you can see that the slope is 0 for the mode, if you can observe. If I can increase the size of this picture. So, you can see that it starts off with of course 0 displacement, but 0 slope also, whereas it is not so for the edges that are x constant. Okay. Here the slope is non-zero, whereas here the slope is 0, derivative is 0 over here, if you can observe that. So, this is the 1-1 mode. Okay. Control C. Then I will just increment it to 2. So, 2 half cycles in the n direction. So, along this 2 half cycles and 1 half cycle along this, but same boundary conditions, 0 slope, okay, slope free and slope free, and 0 displacement all over. And now you have a node line. You have a line along which there is 0 displacement called the nodal line. Okay. So, the high amplitude points are called antinodes, the 0 displacement point or line are called node points or nodal lines. Okay. So, let us see if I do 3-2 mode, M is 3, N is 2, which means 3 half cycles along X. Okay. So, I have 3 half cycles along X, you can see it when the amplitude is low. Okay. So, 3 half cycles and then 2 half cycles along Y direction. Okay. So, the mode shape satisfies the plate PDE, okay, and the mode shape satisfies all the boundary conditions. So, this is very powerful, it is a very powerful shape. Okay. You need to remember this, because later when we try to approximate mode shapes, then we will find shapes which do not satisfy all the boundary conditions, but they satisfy some of them. Okay. So, let me close this animation portion here. So, let us get back. Okay. So now we have looked at rectangular plates. Okay. So now we can look at the next in our system is a circular plate. Circular plate. Okay. For a circular plate, we again have to specify A1, A2, R1 and R2. Okay. It can also be looked upon as a surface of revolution. So, if I have this as my axis and this as my meridian, okay, then this meridian rotates and generates the circular plate. So, the radius of curvature of the meridian is R1 equal to infinity, and its intersection point with the axis is also infinity. So, R1, R2 are infinite. Okay. Whereas, if I now draw the plate, circular plate, okay, and this is the first axis alpha 1, which I call as R. Okay. So, that is already in the form of a length unit, and therefore, A1 is 1, whereas the other coordinate you get when you rotate the meridian, which is theta. Okay. This angle, this is theta now. Okay. Now, at any radius, in order to make this a length unit, you need R. Okay. So, you need R d theta. Okay. So, if you want to go back to ds square, it is A1 times dr square plus A2 times d theta square. So, A2 is equal to R. Okay. So, A1 is equal to 1, A2 is equal to R, R1 is equal to R2 is equal to infinity. That is your circular plate. Okay. Maybe in the next class or the following class, what I will do is I will show you a symbolic set of a symbolic package. Okay. I will show you one symbolic package. You can get hold of any symbolic package in which you can plug in the general set of equations. General set of equations. After that, if you just specify A1, just specify on the top A1, A2, R1 and R2, then it will generate all the relevant equations. It will generate, if you want, only in terms of resultants, and or if you want in terms of displacements, it will do that also. Okay. That is the big advantage. Now, you do not have to struggle to the the general set of equations, substituting this and that, and you don't, in one shot you have already gone through that too many times. So, you plug your A1, A2, R1, R2 into the program, and out will come the set of equations. Okay. I will show you that maybe in the next class. Okay. So, now let us assume for now that we have done that. Okay. And then we get our equation of motion in the u3 direction, okay, the transverse direction, and that looks like this: capital D, the bending stiffness, del 4 u3, which is now a function of r comma theta Okay, alpha 1 is r, alpha 2 is theta. Okay, plus the inertial term del 2 u3 r comma theta comma t del t square is equal to 0. Okay, where del square, okay, is given by del 2 del r square plus 1 over r del by del r plus 1 over r square del 2 del theta square. Okay. So now if that is the case and we substitute now u3 r comma theta comma t as some capital spatial form r comma theta and the frequency term, because we are looking for a harmonic solution. Okay, if we do that, then we get d del 4 u3 r comma theta minus rho h omega square u3 r comma theta equal to 0. Okay, again remember, if we set lambda fourth as rho h omega square by capital D, okay, then this can be written as del to the power fourth minus lambda to the power fourth operating on u3 of r comma theta is equal to 0, or we can write this as del square plus lambda square into del square minus lambda square u3 of r comma t equal to 0. Okay, so what that means is this operating on this can be 0 or this operating on that can be 0. Okay, so both of them will solve this equation. So what are those two cases? Del square plus lambda square is 0 and del square minus lambda square u3 is also 0. Okay, so now what do we do? Now what we do is my u3 of r comma theta, I will again try to work out a separable solution r of r into theta of theta. Okay, and substitute in each of these. Substitute in each of these. So let's see what we get. If we do that, then we get del 2 del r square r of r theta of theta plus 1 over r del r r of r theta of theta plus 1 over r square del 2 del theta square r of r theta of theta plus or minus lambda square r theta equal to 0. Okay, we are just about run out of time, so I will stop it here. We will continue from here in the next class. Okay. Thanks.